AQA A-level physics. This is for the medical physics option, and this video is about endoscopy. So endoscopy, you've got a long thin tube and it's passed into your body, usually through a natural opening such as your mouth or your bum or whatever, and this allows a doctor to see inside your body, to diagnose problems, to see what's wrong, perhaps to take a biopsy, which is like a sample, or sometimes to help carrying out some operations as well, keyhole surgery. Examples include colonoscopy, gastroscopy. So there's a guy getting an endoscope in his gob. Now, light travels through an optical fibre. Most of this is either GCSE or it's on the core syllabus. You have the cladding and the core. So they're both transparent, but the important thing is that the refractive index of the cladding is less than the core. So we get total internal reflection taking place. Now, normally light travels in a straight line. So how do you get light to travel through a tube? And the answer is by total internal reflection. So this is our fiber optic cable, yes, our glass fiber, and you can see we've got the bit in the middle, and then you've got the cladding on the outside, and the ray of light can go bounce, bounce, bounce inside and come out the other end. There would be one equation you might have to use. Now, normally from GCSE, sine C equals 1 over n, but here we've got two values of n, so it's the lower value over the higher value, so n cladding over n core. This diagram isn't to scale. A single typical endoscope fibre, the diameter of the cladding 125 micrometers, which is about 1/10 of a millimeter, and then the diameter of the core is like less than 1/10 of that. So very, very thin fibres, and a typical endoscope may contain up to about 7,000 fibres. Now, there's two types of cable which contain lots of fibres. You've got a coherent bundle and a non-coherent bundle. If you want an image, then you need a coherent bundle, which basically means that the relative positions of the fibres are the same at both ends. The end that you look in, which is the eyepiece, and then the end that the light enters, which is the objective. There would be lenses on top of these ends as well, so that everything's nice and focused. But if you look at this, it's not a digital image because the light intensity is continuous for each particular fibre. And you can also get a colour image as well. So it's certainly not digital, but for each fibre, it's in the same position at both ends. And that is a coherent bundle. And if you actually want an image, then you need a coherent bundle. This is a typical endoscope. Pinched a couple of diagrams off the internet. A typical endoscope will contain a coherent bundle of fibres with an objective lens to focus the image. So your coherent bundle there's the objective lens there. Okay. Is that another one as well? Confocal imaging window. Several non-coherent bundles, and they're just for light. It's actually quite dark inside your body. It's very dark inside your stomach. So if you need to see what's going on, then you need to kind of light it up. So you have a couple of bundles which just put light into your body so that you can see what's going on. Yeah, and they're non-coherent bundles. Perhaps there's some air and water nozzles as well. Perhaps there's an instrument channel. As I said, for surgery, maybe like little clippers and things come out, or little crocodile clip comes out and grabs hold of something. So this is a typical endoscope. We'll compare different techniques in a later video, but for now, compared with other imaging techniques, you get clear real-time images, and it's very, very safe, It's non-ionizing, unlike X-rays and using radioactive isotopes.